A 100,000-ton aircraft carrier cannot dodge a Mach 5 weapon. That is the starting constraint. A Nimitz-class carrier displaces roughly 100,000 tons of seawater and stretches over 1,000 feet of steel across the ocean's surface. Hydrodynamic drag in water is unforgiving. Acceleration takes time. Rudders take time. In contrast, an anti-ship ballistic missile descends from the upper atmosphere at hypersonic speed during its terminal phase. The engagement window is measured in minutes, sometimes less. From a purely mechanical perspective, the carrier cannot simply throttle forward and steer away from danger. The mathematics does not allow it. This is the paradox that defines modern naval warfare. If the enemy knows the precise coordinates of a carrier strike group, and if a ballistic weapon can arrive at Mach 5, then the physical size of the target becomes a liability. A Nimitz-class hull presents an enormous radar cross-section. It is effectively a floating city. You cannot hide that amount of steel with camouflage paint or clever angles. Physics guarantees that radar energy striking a carrier will produce a measurable return. If a radar network can maintain a continuity the city, but modern naval combat is not solved at the level of raw mechanics. It is solved at the level of systems. A missile does not simply fly toward a ship on instinct. It relies on a chain of sensors, processors, communications links, and guidance updates. Engineers refer to this sequence as the kill chain. The missile is only the final physical component of a much larger architecture that begins with detection and ends with terminal guidance. Break any link in that architecture and the weapon becomes blind. It continues flying, but it no longer supposed. This is why the survival of a carrier strike group is rarely determined by armor thickness or maneuvering speed. The decisive layer sits above the waterline, inside the electromagnetic spectrum. Radar networks, data links, electronic warfare platforms, and command and control systems determine whether the enemy ever receives the information required to generate a firing solution. In other words, the carrier does not have to outrun the missile. It only has to disrupt the equation that tells the missile where to go. To understand how this works in practice, we have to look at geography. Not maps in the civilian sense, but the geometry of strike range, sensor coverage, and engagement envelopes. The location of a carrier strike group is never accidental. Every nautical mile is a calculation. On a map, the waters of the North Arabian Sea and the Gulf of Oman appear empty. For a civilian observer, it is simply open ocean. For a naval strategist, it is a geometric problem defined by range rings and sensor coverage. The position of a carrier strike group in this region is not symbolic. It is mathematical. Carrier aviation and cruise missiles are constrained by distance. A Tomahawk Block 5 cruise missile can travel long distances, but every additional nautical mile reduces the flexibility of the strike plan. Aircraft launched from a carrier deck face even tighter limits. Fuel load, payload weight, and time over target all interact. If the carrier remains too far from the theater, the strike package becomes inefficient. Aircraft must dedicate more fuel to transit, reducing the weapons they can carry and the time they can spend in contested airspace. The solution is straightforward but risky. The carrier must move closer. Closing the distance allows the carrier air wing to operate within effective strike range of inland targets and naval bases along the Iranian coastline. It also allows destroyers within the strike group to launch cruise missiles along more efficient trajectories. From an operational standpoint, this proximity dramatically increases the tempo and effectiveness of strike operations. However, the same decision introduces a critical trade-off. By moving closer to the coastline, the carrier strike group enters the theoretical engagement envelope of Iran's integrated air defense system. This system, commonly referred to as the IADS, is designed specifically to monitor and contest airspace across the region. It is not a single radar station or a single missile battery, it is a network. Iran's IADS combines multiple radar platforms and missile systems into a layered architecture. Domestic Bavar 373 systems form part of the outer defensive ring. Russian-supplied S-300 PMU-2 batteries add additional long-range coverage. At the center of this architecture sits the S-400 radar and engagement system, capable on paper of tracking large numbers of targets simultaneously across hundreds of kilometers. These systems rely on radio frequency energy. Radar transmitters emit pulses that travel through the atmosphere until they strike a physical object. A portion of that energy reflects back toward the radar receiver. By measuring the time delay and signal characteristics of that reflection, the radar system can determine range, velocity, and direction. This is where a supercarrier becomes difficult to hide. The radar cross-section of a Nimitz-class carrier is enormous. Even as radar energy weakens over distance according to the inverse square law, the sheer scale of the carrier ensures that enough reflected energy returns to the radar receiver to generate a track. The echo may be faint, but it is still detectable. From the perspective of physics, the radar will see the carrier. This leads to an uncomfortable conclusion. If the radar network remains functional, and if it maintains a reliable track, then the enemy possesses the first critical link in the kill chain. Detection leads to targeting data. Targeting data leads to weapons launch. The carrier cannot rely on physical concealment to avoid this outcome, so the United States Navy approaches the problem from a different angle. If the radar echo cannot be prevented, then the system receiving the echo must be disrupted. That shift moves the battle away from steel hulls and into something far less visible, the electromagnetic spectrum. If the radar echo cannot be prevented, the logical solution is not to hide the carrier. The logical solution is to attack the network that interprets the echo. Modern integrated air defense systems are not isolated machines. They are distributed architectures built from sensors, data links, command nodes, and missile batteries that exchange information continuously. A radar dish alone does not win a battle. The network behind it does. Before the first aircraft launches from the flight deck of CVN-72, the architecture of that network has already been studied in detail. Cyber operators and intelligence agencies spend years mapping the digital structure of an integrated air defense system. They analyze communication protocols. They identify data handshakes between radar nodes and command centers. They observe how tracking data flows from sensors to missile batteries. This process creates a digital map of the enemy's nervous system. The purpose of that map is not simply intelligence. It allows the attacking force to understand where information originates, where it is processed, and where it becomes actionable targeting data. In a networked defense system, early warning radars feed data to command posts, which then distribute tracking information to missile launch units. Disrupting any portion of this chain introduces delays and uncertainty. Once those radar emitters and communication nodes are identified, their coordinates are integrated into the strike group's tactical systems. The data becomes part of the electronic order of battle. Electronic warfare aircraft do not enter the battle space blindly. They approach with precise knowledge of which frequencies are active, which radar types are operating, and where those transmitters are located. This is where the EA-18G Growler becomes central to the operation. At first glance, the Growler appears similar to the F/A-18 Super Hornet airframe from which it is derived. In reality, it represents a very different design philosophy. Bomb racks and large kinetic payloads are replaced with electronic warfare pods and specialized receivers. The aircraft sacrifices explosive firepower in exchange for control over the electromagnetic spectrum. Mounted within the Growler's electronic warfare suite is the ALQ-218 receiver system. Its function is to scan the airspace continuously for radar emissions. Every radar transmitter has a unique signature defined by frequency, pulse repetition, and modulation pattern. The receiver analyzes these characteristics in real time, allowing the aircraft to identify exactly which radar systems are operating and where they are located. Once those signals are detected and classified, the Growler can respond with targeted jamming. Importantly, this jamming is not the crude broadcast interference used in earlier generations of electronic warfare. Instead of flooding the entire spectrum with noise, the aircraft concentrates energy into narrow directional beams. The objective is not to blind the entire battle space. The objective is to create specific corridors where radar tracking becomes unreliable. The physics of the situation favors the jammer. Radar systems depend on two-way signal propagation. Energy must travel from the radar transmitter to the target and then return to the receiver after reflection. Each leg of that journey weakens the signal. In contrast, a jamming transmission travels in only one direction, from the aircraft directly to the radar receiver. Because of this asymmetry, the energy density of the jamming signal arriving at the receiver can exceed the strength of the reflected radar echo. When that occurs, the radar's tracking solution collapses. The receiver can no longer distinguish the real reflection from the background interference. Targets disappear from the screen or appear at incorrect positions. In practical terms, this creates electronic corridors through which strike aircraft and missiles can pass with greatly reduced risk of detection. But electronic suppression introduces another dilemma for the defender. Radar operators must decide whether to keep transmitting or shut their systems down. Each option carries consequences, and this decision leads directly to the next stage of the operation. For radar operators inside an integrated air defense system, electronic warfare creates an unsolvable decision. If they shut their radars down, they avoid being targeted by anti-radiation weapons. But they also lose the ability to see the airspace they are responsible for defending. Without radar emissions, the entire network becomes blind. Aircraft and cruise missiles can pass through undetected. If they keep their radars active, they regain visibility. However, the act of transmitting radio frequency energy reveals their exact position. Radar transmitters are powerful sources of electromagnetic radiation. In a modern battle space filled with electronic surveillance receivers, those emissions are impossible to hide. This dilemma forms the core vulnerability of radar-based defense systems. The very act of sensing the battle space exposes the sensor itself. Electronic warfare aircraft exploit this vulnerability by forcing radar operators into a reactive posture. As Growlers inject jamming energy into the radar frequencies used by systems such as the S-300, S-400, and Bavar 373, radar operators may attempt to overcome the interference by increasing transmission power. From their perspective, a stronger signal might burn through the noise. But this response has an unintended effect. Increasing radar power turns the radar transmitter into a brighter beacon within the electromagnetic spectrum. That beacon can be detected and precisely located by electronic support systems operating across the strike force. Once that emission is identified, another class of weapon enters the equation: the anti-radiation missile. Weapons such as the AGM-88 HARM and the more advanced AAR-GMER are specifically designed to track radar emissions. Instead of searching for a physical target using onboard sensors, these missiles simply follow the radio frequency energy being transmitted by the radar. The radar itself becomes the guidance signal. As long as the radar continues to emit, the missile has a path to follow. This dynamic transforms suppression of enemy air defenses into destruction of enemy air defenses. Initially, electronic warfare disrupts radar tracking and degrades the effectiveness of the network. Once radar operators react by transmitting more aggressively, anti-radiation missiles can be launched to physically destroy the emitting antennas. The result is a cascading effect across the air defense architecture. Individual radar sites are disabled or forced offline. Communication between sensor nodes becomes unreliable. Missile batteries lose the targeting data required to guide their interceptors. The network begins to fragment. Integrated air defense systems rely on coordination. Long-range radars provide early warning. Fire control radars provide precise targeting data. Command centers distribute information across multiple batteries to ensure overlapping coverage. When electronic attack and anti-radiation strikes remove key nodes from this architecture, the system loses its cohesion. What remains are isolated radar stations and missile launchers, operating without reliable situational awareness. At that moment, the defensive grid transitions from a coordinated network into a collection of disconnected sensors. And once that network collapses, the operational environment changes completely. The battle space opens. Once the radar network begins to fracture, the character of the operation changes. Electronic warfare alone does not achieve the strategic objective. Its role is to create the conditions for kinetic strike operations. When the integrated air defense system loses coordination, a temporary window appears in which aircraft and missiles can move through the battle space with reduced risk. Inside the carrier strike group, this transition activates the next layer of the kill chain. Several hundred miles offshore, Arleigh Burke-class destroyers within the strike group prepare their Mark 41 vertical launch systems. Each destroyer carries dozens of launch cells capable of firing a range of weapons. In this phase of the operation, the primary tool is the Tomahawk Block 5 cruise missile. Tomahawks are designed for long-range precision strikes. Unlike ballistic missiles, they travel at subsonic speeds and follow terrain-contoured flight paths. Their guidance systems rely on a combination of inertial navigation, GPS updates, and digital terrain mapping. Because of this guidance architecture, Tomahawks can navigate complex routes through partially degraded radar environments. The electronic corridors created by the Growlers now become essential. With key radar nodes disrupted and communication links degraded, Tomahawks can pass through gaps in the defensive network while maintaining accurate navigation toward their targets. At roughly the same time, the carrier itself launches aircraft from its flight deck. Among the first to enter the contested airspace are F-35C Lightning II fighters assigned to the carrier air wing. The design philosophy of the F-35C differs significantly from that of earlier naval aircraft. Its airframe and materials reduce radar cross-section, allowing it to operate inside radar coverage zones with a lower probability of detection. In this operation, the F-35Cs serve as forward elements of the strike architecture. Their mission is not large-scale bombing. Instead, they sanitize the airspace ahead of the main strike force. Air-to-air missiles, such as the AIM-9X, are carried within internal weapons bays to preserve the aircraft's low observable profile. If hostile aircraft attempt to intercept the strike package, the F-35s are positioned to neutralize the threat. Following behind this stealth vanguard are F/A-18F Super Hornets from strike fighter squadrons operating aboard the carrier. Unlike the stealth fighters, the Super Hornets carry external payloads of precision-guided munitions. These aircraft deliver joint direct attack munitions, typically in the 500-pound class, against naval infrastructure and surface vessels. The effectiveness of this strike architecture depends on timing. Cruise missiles launched from destroyers and aircraft-delivered munitions must arrive over their targets within carefully calculated windows. When impacts occur simultaneously across multiple locations, the defender's ability to react becomes limited. In practice, this means that Tomahawk cruise missiles approaching at low altitude and strike aircraft releasing guided bombs from above converge on their targets within seconds of each other. Naval bases, piers, and moored warships become exposed once the air defense network is disrupted. Locations such as Bandar Abbas and Kanarak serve as major naval facilities along the Iranian coastline. Warships moored alongside piers present relatively static targets compared to vessels maneuvering at sea. If those ships remain concentrated in port rather than dispersed across multiple locations, the strike force can generate significant damage in a short period of time. Under these conditions, the balance of the engagement shifts rapidly. Ships at anchor have limited ability to maneuver or defend themselves against incoming precision strikes. When multiple weapons arrive nearly simultaneously, the probability of successful hits increases dramatically. The result is the physical phase of the operation: cruise missiles and guided bombs striking naval infrastructure and surface combatants. However, destruction of fixed targets does not end the engagement. Military systems possess inertia. Even when significant damage occurs, the opposing force retains the ability to respond. And in this scenario, that response arrives in the form of a different class of weapon entirely. The destruction of naval infrastructure does not end the conflict. Military systems rarely collapse instantly. Even after suffering significant losses, an opposing force can still retain the capability to retaliate. In this scenario, that retaliation takes the form of anti-ship ballistic missiles launched by the Islamic Revolutionary Guard Corps. Ballistic anti-ship weapons represent a fundamentally different threat compared to cruise missiles or aircraft. Instead of traveling through the atmosphere at low altitude, these missiles follow a ballistic trajectory that carries them high above the Earth before descending toward their target during the terminal phase. As they fall back toward the ocean, their speed can exceed Mach 5. At those velocities, interception becomes difficult. Reaction time shrinks dramatically, and the energy of the descending warhead increases the destructive potential of even a near miss. However, the effectiveness of a ballistic anti-ship missile depends on far more than raw speed. The weapon itself is only one component of a much larger targeting architecture. To strike a moving carrier at sea, the attacker must complete a sequence of steps often described as a kill chain. The first step is detection. Sensors must identify the presence of a carrier strike group somewhere within the ocean battlespace. This can involve radar surveillance, maritime patrol aircraft, satellite observation, or other reconnaissance systems. Once the target is detected, the next step is determining its precise location. A carrier strike group is not a stationary installation. It is a formation of ships that continuously maneuvers to complicate enemy targeting. Generating accurate coordinates requires persistent tracking and continuous updates. Those coordinates must then be transmitted to the missile launch unit. This stage introduces another potential point of failure. Communications networks must function correctly under conditions of electronic warfare, cyber interference, and operational stress. After the missile is launched, the process is still incomplete. During its mid-course phase, the weapon may require updated targeting data if the carrier strike group has changed position. Without these updates, the missile may descend toward a location where the target no longer exists. Finally, during the terminal phase, the missile's onboard seeker must locate and lock on to the carrier within the vast surface area of the ocean. Only at this final moment does the weapon commit to its impact trajectory. Each step in this sequence represents a dependency. Detection depends on sensors. Tracking depends on radar or surveillance assets. Data transmission depends on communication networks. Terminal guidance depends on onboard sensors operating correctly under intense electronic interference. If any link in this chain breaks, the missile continues flying but loses the information required to reach its intended target. This is the systemic vulnerability of ballistic anti-ship weapons. Their speed and kinetic energy make them formidable, but their effectiveness depends entirely on the integrity of the information architecture guiding them. Understanding this dependency shifts the focus of defense away from pure interception. Instead of attempting to destroy every incoming missile physically, the defending force can target the information flow that guides those weapons. And that defensive process begins long before the missile enters its terminal dive. The first response to a ballistic missile launch is not an interceptor leaving a launch cell. It is information. Across the battlespace, multiple sensor platforms monitor the region continuously. Some of these sensors operate in orbit, observing the Earth with infrared detection systems designed to identify the thermal signatures produced by missile launches. When a ballistic missile ignites its rocket motor, the exhaust plume generates an intense burst of infrared energy. From space, that thermal bloom is unmistakable. The moment the launch occurs, that signal is detected. Satellite warning systems relay the event through command networks almost instantly. The data is then fused with airborne sensor platforms operating in the region. Aircraft such as the E-3 AWACS and the Navy's E-2D Hawkeye maintain persistent radar coverage over large sections of the battlespace. These platforms are not simply surveillance aircraft. They function as airborne command nodes, distributing tracking information across the strike group. By combining satellite detection with airborne radar tracking, the carrier strike group gains a crucial advantage: time. Ballistic missiles launched from inland launch sites must travel significant distances before entering their terminal descent phase. Depending on the launch location and trajectory, the flight time can range from roughly 10 to 12 minutes. Within that window, the strike group must analyze the incoming threat and begin defensive measures. During this phase, electronic warfare platforms remain active above the battlespace. The EA-18G Growlers that previously suppressed radar systems do not immediately return to the carrier deck. Instead, they continue operating in orbit, maintaining control over portions of the electromagnetic spectrum. At this stage, the nature of electronic warfare changes. Earlier in the operation, Growlers focused on degrading ground-based radar systems that formed the backbone of the enemy's integrated air defense network. Now the target is different. The objective becomes the guidance system of the incoming missile itself. This is where the next-generation jammer, designated ALQ-249, becomes critical. Modern anti-ship ballistic missiles often rely on onboard seekers during the terminal phase of flight. These seekers may use radar or other sensors to identify large surface vessels within the missile's field of view. As the missile descends toward the ocean, the seeker begins scanning for a target that matches the expected radar signature of a carrier strike group. Electronic warfare systems exploit this dependency. Instead of simply transmitting noise to overwhelm the missile's seeker, advanced jamming systems can manipulate the signals the seeker receives. By intercepting the radar pulses emitted by the missile and altering their characteristics before retransmitting them, electronic warfare aircraft can generate deceptive signals. These signals create phantom targets within the missile's guidance processor. To the missile's onboard computer, multiple large radar returns may suddenly appear across the surface of the ocean. Some may appear slightly offset from the carrier's actual position. Others may appear at entirely different coordinates. The seeker must interpret these signals and determine which one represents the real target. But if the guidance system receives conflicting data, its targeting solution becomes unstable. Instead of guiding the missile toward a precise impact point, the onboard processor begins chasing inaccurate coordinates generated by the deception signal. This process does not physically destroy the missile. The warhead remains intact. The propulsion system continues functioning. The missile simply no longer knows where the carrier actually is. And while the missile's guidance system struggles with this distorted picture of the battlefield, the carrier strike group continues executing its own defensive geometry. While the missile's onboard seeker struggles to interpret conflicting signals, the carrier strike group executes its second defensive layer, geometric relocation. A Nimitz-class carrier is powered by 2 nuclear reactors that drive massive steam turbines connected to 4 propeller shafts. When operating at full power, the vessel can exceed 30 knots. That speed may appear modest compared to aircraft or missiles, but over the timescale of a ballistic missile flight, it becomes operationally significant. Ballistic missiles launched from inland positions in Iran must travel several hundred nautical miles before reaching the waters of the Gulf of Oman or the North Arabian Sea. Even at hypersonic velocity, the total flight time typically ranges between 10 and 12 minutes. During those minutes, a ship moving at flank speed can cover several nautical miles. If the carrier travels at approximately 30 knots, it moves roughly half a nautical mile per minute. Over a 12-minute interval, that displacement can exceed 6 nautical miles from its previous coordinates. In the open ocean, this distance is substantial. A ballistic weapon descending toward a point in space that no longer contains its target will simply strike water. This maneuver is not random. Carrier strike groups rarely travel in straight lines for long periods. Constant course changes and speed variations complicate enemy targeting calculations. When combined with electronic deception affecting the missile's seeker, these movements increase the uncertainty of the impact point. In other words, the missile is attempting to intercept a location that is already outdated. Meanwhile, the carrier does not operate alone. Escorting destroyers equipped with the Aegis combat system form an additional defensive layer around the formation. These Arleigh-Burke-class ships carry vertical launch systems loaded with interceptor missiles capable of engaging ballistic threats. Two primary interceptors are available within the Aegis arsenal. The SM-3 is designed to intercept ballistic missiles in the exo-atmospheric phase of flight, outside the Earth's atmosphere. It relies on kinetic impact to destroy incoming warheads before they descend toward their targets. The SM-6 provides an additional layer of defense within the atmosphere during the missile's terminal phase. These interceptors represent the hard kill option. However, the use of interceptor missiles introduces a logistical constraint. Each destroyer carries a limited number of vertical launch system cells, typically 96. Those cells must accommodate a variety of weapons, including surface-to-air missiles, anti-submarine rockets, and cruise missiles. Every interceptor launched reduces the remaining defensive inventory of the strike group. In a high-intensity conflict, firing multiple interceptors at every incoming threat could rapidly deplete the magazine. For this reason, electronic warfare and deception remain the preferred first line of defense. If the incoming missile can be diverted or confused before reaching its terminal targeting phase, the strike group avoids expending valuable interceptors. In this engagement, the combination of electronic deception and geometric relocation proves sufficient. The missile's seeker, influenced by false signals, guides the weapon toward incorrect coordinates. At the same time, the carrier has already moved away from the position used in the original targeting data. When the ballistic missiles descend through the final stage of their trajectory, they encounter empty ocean. No interception is required. The warheads impact the water without ever approaching the carrier's actual position. From the outside, the outcome appears deceptively simple. 4 ballistic missiles descend toward the ocean and strike nothing but water. Public statements may claim otherwise, but the physical result remains unchanged. The carrier strike group continues operating in the region. The explanation for this outcome does not lie in armor thickness or defensive gunfire. Instead, it lies in the structure of the system that produced the missile launch in the first place. Ballistic anti-ship weapons are often presented as unstoppable because of their speed. Hypersonic velocity compresses reaction time and complicates interception. However, speed alone does not guarantee a successful strike. A ballistic missile must still solve the targeting problem of hitting a moving object across hundreds of nautical miles of ocean. That problem is fundamentally informational. To strike a carrier at sea, the attacker must maintain an accurate track of the target from the moment of detection until the moment of impact. Sensors must locate the carrier. Communications networks must deliver those coordinates to the launch unit. Guidance systems must update the missile's trajectory during flight. The terminal seeker must distinguish the carrier from the surrounding ocean surface. Every step depends on clean, reliable data. When electronic warfare disrupts radar tracking, when cyber operations degrade communication networks, and when deception signals inject false targets into missile seekers, the information flowing through that chain becomes unreliable. The missile itself continues functioning exactly as designed, but the data guiding it no longer corresponds to reality. In effect, the weapon is operating inside a distorted version of the battlefield. This is why control of the electromagnetic spectrum has become central to modern naval warfare. Ships, aircraft, and missiles remain the visible elements of military power, but the decisive interactions increasingly occur within radio frequencies and data networks. Sensors detect, processors interpret, communications links distribute information across the force. If that informational architecture collapses, the physical weapons connected to it lose their effectiveness. For the carrier strike group, survival depends on maintaining dominance within that invisible layer of the battle space. Electronic warfare aircraft, airborne command platforms, cyber operators, and networked sensors work together to shape the information environment surrounding the fleet. When those systems function effectively, the enemy's targeting process becomes unreliable long before a missile enters its terminal dive. And this brings the analysis back to the original paradox. A carrier cannot outrun a Mach 5 weapon, but it does not need to. If the attacker cannot maintain a stable targeting solution, the missile will never arrive at the correct coordinates.